Welcome to Ask and Learn.
In this problem, a number of aluminium balls are to be quenched in a water bath at a specified rate. We need to calculate the rate at which the heat needs to be removed from the water in order to keep its temperature constant. We assume that the thermal properties of the balls are constant, the balls are at a uniform temperature before and after quenching, and the changes in kinetic and potential energy are negligible. Now, the properties of the aluminium balls are at the average temperature, which is the temperature at the middle of the initial and final temperatures, which is 370 Kelvin. We have the density of the aluminium balls to be 2,700 kg per cubic meter, and the specific heat, C, to be 0.937 kilojoule per kg degree Celsius. Now we'll take a single ball as the system. So we can write the energy balance equation for this closed system as E in minus E out is equal to the change in the energy of the system, delta E. Now we only have energy leaving the system in the form of heat, as the balls lose heat to the water. And this is equal to a change in the internal energy of the ball, delta U. So we can write this as mc T1 minus, or T2 minus T1. And this is because we can write delta U as m into U2 minus U1, the mass specific change in internal energies, and we can write that as mc T2 minus T1. So if we multiply both sides by minus 1, we get that the heat out of the ball and into the water, Q out, is equal to mc T1 minus T2. So we multiply both sides by minus 1. Now, in order to be able to use the energy balance equation, we first need to find the mass of the aluminium ball. The mass of the ball is its density times its volume, rho v. So that's rho, and this is a sphere, so its volume is 4/3 pi r cubed. But we don't have the radius r, we do have the diameter d. So it's pi d cubed over 6. Remember, the diameter is twice the radius. And these values are all known. So if we substitute them in, we get this to be 2,700 SI units, kg per cubic meter, times pi times diameter of 0.05 meters, and suppress the units here, and that's cubed, over 6. So we get a mass of a single ball to be 0.1767 kg. Now that we have the mass, we can put this mass back into our energy balance equation. So this gives us the heat transfer from one ball to the water, Q, is equal to mc into T1 minus T2. So again, we can substitute values in here. That's 0.1767 kg for the mass times the specific heat of 0.937, that's kilojoule per kg degree Celsius, times a change in temperature of 120 minus 74 degrees Celsius. And so we get the energy, the heat transfer from one ball to the water is 7.62 kilojoules. Now we have the energy for one ball that gets transferred into the water in terms of heat. We can then find the total rate of heat transfer from the ball to the water, Q dot, is equal to the number of balls passing through the water, dn dt or n dot, times the value for one ball. And we know this rate is 100 balls per minute multiplied by Q from above is 7.62 kilojoules of heat energy transferred to the water per ball. Hence, we get the total rate of heat transfer from the balls to the water to be 762 kilojoules per minute.